Right, let's get started. Welcome back, everybody. A nice long break for me for a few days. Hope you're feeling pretty good about midterms. Next thing we're gonna start doing up here is obviously, now we're gonna start jumping into statistics. Okay? Things are gonna start taking a shift. You're gonna start noticing things, you're gonna start, progressing toward a different way now. Okay? Not a bad one. Okay? I always think, well, the second half of class is a little bit more abstract. I always feel it gets a little, we're gonna do a lot of repetition. What you're gonna see in chapter 6 is inherently, if I could put this out, but bluntly, it doesn't aid to your knowledge of statistics. You will never use any of this in statistics. But what this will be considered is proof of concept. Because if you don't have a proof of something or a reason to say, yes, I know this works, then why are you doing it? Okay? And that is really what's going to be happening in this first little, basically chapter 6:1 through 6:5. It's going to be saying, hey, this works because X, Y, Z. So that when we actually start doing statistics in 7, 8, 9, and 12, you can go, well, this works because. We can point back and go, it works because of this right here. And that's why. So 6:1, we're gonna get through 6:1 today for sure. We'll start on 6:2. If you don't have your books, it's okay. Your books are not, you don't have to have them. I'm gonna show you how to do stuff on your calculator later. But some people do become partial to the book at this point, okay? See that Miss Weed over there has hers. I may steal yours here in a little bit, Mel, just to kind of show everybody what I'm talking about. It'll be for 6:2. But that way, I do have it on the PowerPoint as well. You can kind of talk about, but I want you to see where it's in the book. Okay, so introduction to normal distribution. Remember, a distribution is literally just you have data. Okay, things tend to clump in certain areas. That clump we consider our mean, and then from there things go out. Okay. So we're now going to start talking about normal distribution. And by going with normal distribution, I have to pull it up on YouTube. I'm going to show you a game. It's an old game show. Maybe you've seen it. Who knows? And I want you to look at it. It's about 2-3 minute video. It's funny. The lady is quite annoying in it. Okay. And I'm glad she walked with me. But still, let me kind of show you here. And I'll skip through. What is Plinko? Fair to the Price is Right. Good. Yeah, see, somebody has. The rest of you, y'all kind of suck. So let me show you what the price of right is here. Come over here to right. This video is gonna play today.
It's Big Money Week. It's our first contestant.
Yeah.
What do we got for her?
You are gonna play Plinko for a chance to win up to $1 million.
Wow. Lisa, come on over here. Wow. Lisa. You like this game?
Yes, of course.
How about $1 million Plinko? You like that even more?
I'm gonna have a heart attack, but
Yeah. Grab a Plinko chip because you get one Plinko chip just for playing the game. And that one Plinko chip alone is worth up to $200,000 in your hand right now.
What?
You can win up to 5 chips. Now, here's how you win the chips. We have some small prizes over there by beautiful Big Money Rachel. George, start us out, please.
All right, here we go. First up, this battery-powered touchless automatic soap dispenser features an infrared motion sensor for easy and accurate dispensing.
Does the price start with a 7 or end with an 8?
I think it starts with a 7.
Starts with a 7. It is 74 bucks. Another
Glad she
chip
lost.
worth up to $200,000. You want to grab the other chip? Go ahead.
Thank
Let's
you.
grab them as we go. Next one, please.
All right, second, this dishwasher-safe glass carafe holds up to 6 cups of filtered water.
So it's a glass carafe. Does the price start with a 4 or end with a 0?
I think it ends with a 0.
What y'all
Ends
think?
with a
Zero?
0,
Yeah.
please.
Does it?
Think so?
No, $49.
It's cool.
That's it. That's okay. Next one, please.
Yeah.
Get him back.
Here we go. Third, this handheld steamer has a 40-second heat up time and 2 output settings.
Is the price of that start with a 9 or end in a 0?
I think it ends in a 0, Drew.
Ends with a 0.
Yeah.
It is $60.
Oh,
Grab another chip.
Thank you.
Let's
very
get a
much.
4th chip, Lisa.
do it.
Let's get a 4th chip. Go ahead,
Okay.
George
Here we
and
go.
Rachel.
Finally, great for multi-purpose use, this electric scrub brush has an ergonomic handle and an LED charging indicator.
how
Answer
dirty
the
are
show
you
with
that
that
you
one.
need that
Lisa,
scrub brush?
does it start with a 3 or end with a 9?
Ooh, I think it ends with a 9.
Ends with a 9. It is. No, it's only $36. Well, you know what? You have 3 chips, each one worth up to $200,000. Go on up the stairs, Lisa. Good luck to you.
Watch this part. Let me ask
There
you a
she
question.
goes.
This is kind of the part
Hopefully,
we
you
want to
should
look
get
at.
one of those chips in the middle. So, Lisa, one by one, put the chip up against the wall, let it drop. $200,000 in the middle. Good luck to you. There's the first one, drops it under the K. Come on in, come on in, come on in. We get $1,000. Not for nothing, $1,000.
Okay. All right.
If
And
it was a big money week, that would have been only $500. Now she's going over by the.
I broke Plinko.
Reach your hand down there and just tap it. There you go. Perfect. $1,000 again. We really want the $200,000 in the middle. Go ahead, Lisa.
I pay taxes.
Here we go. It's coming down fast, and it's miles above you. Oh no, $2,500. Well, you know what? $4,500. Not bad.
Look here. Now tell me something. First off, I'm glad she didn't win a lot of money. She was annoying me. But look at it carefully. Now, barring the fact that, first off, they add a little bit of unpredictability to it. Do you see the unpredictability? What is it? The bounce. It's got a slight bounce. Okay, when the Plinko hits, you see that little slight bounce it does? That makes a little bit of unpredictability, okay, which is fine. But what if I got rid of that and I just gave you this? Plinko hits. Go again this. Plinko hits, it's got to go where? Left or right? Okay, well, what are the odds of it going left?
50%.
What's the odds of it going right?
50.
But then it's got to hit another Plinko. Now what? Or another junction, right? What are the odds? 50, 50. What are the odds again? Again. You see what's happening here? Now go back to your tree diagram. Remember whenever you did the flipping of the coin? Every single hit is just a decision that thing had to make. Am I going to go this way or this way? Am I going to go this way or this way? Now, mind you, barring the fact that, yes, it does bounce, okay? That does add a higher level of unpredictability than you've got, you know, fluid forces, and that's all physics. But if we just went directly, let's just keep it simple, 50-50, okay? Keep that in your mind today, okay? There is a method to my madness, I promise you, okay? So. What is Plinko? Now you know, you can go home and tell people, I know Plinko is new. But as we get started, remember, this week, pretty much week and a half after spring break, this is proof of concept, okay? I have to ask you to believe me, and I'll show you mathematically, but I want you to take some things on faith right now, and then we'll kind of take care of it. Okay, I will show you mathematically. I will show you not mathematically, I'll show you things in the physical world. I can't show you mathematically. Okay, I can if you really want to see it. But it's gonna just get convoluted, okay? But let's go back to my example. I've given you a lot of times. If I left here at this zip code or whatever, city limit, and I drove to another city limit, 100 miles away, okay? Remember me saying this? And I said, hey, what are the odds of a wreck happening? in that 100 miles. It's 100%. It's gonna happen. Okay, but now I said to you this, what are the chances of a wreck happening exactly at mile marker 95 miles and 3 inches? That's almost 0%. Did you agree with that? I mean, we're getting really exact with our numbers. I say that because you kind of have already done that. If you go back to your probability that you just learned, that probability distribution that in 5-2, didn't you take a bunch of probabilities, put them in a table and say, hey, what's the probability of this happening right here? Remember when it says exact? Or what's the probability of this happening and before? But they were still countable. Notice I can roll a dice and go, I know 6, they were this many times, or I'm selling houses this many times, right? It was countable. Somebody wasn't selling a house an infinite amount of times. There was a finite we could count it. But what happens to your probabilities when they reach infinity levels? I mean, we're talking, remember, at the very beginning of learning about probabilities, we learned about the law of large numbers. What happens to things as they get large? Things tend to start molding into a shape. We start getting distributions out of it, okay? So that's kind of what's happening, not kind of, this is what you're gonna start seeing today. So with what we're learning with normal distributions, you can understand how meteorologists predict the amount of rainfall in a given month or over a month. Stock prices, if you have stocks, I feel bad for you today because of what the stock market did yesterday, okay? How do coaches analyze athletic performance? And also the probability that person's income falls within a specific range. All of these can be described by normal distribution. All of them. Yes. The astute student will leave here, Google some stuff and go, did you know there's other distributions? Yes, there is. You'll learn about 2 more in this class. Okay, but one that happens in nature a lot is what we call a normal distribution. You've already been dealing with it. You've been dealing with it a lot. Okay. So let's look at it. We are now beyond discrete random variables. We're now moved into continuous random variables. And a continuous random variable is a variable whose numeric value is determined by the outcome. And I want you to really pay close attention to this statement right here. Let me get my highlighter right here. Probability experiment. That is very important, okay? So here, as you can see, I clicked on this, a normal distribution of a sample of 500 randomly selected adult men in the United States. Okay? Randomly selected, doesn't tell us what kind of sampling system they use, but we know that they use one. Okay, let me get my pen here. Okay. Look at the graph. Remember, they took a sample, right? Recorded, took a sample, recorded, took a sample, recorded. They kept doing it over and over again, and they got this distribution. Well, that should look like something to you, doesn't it? You've seen this distribution. Remember whenever you start doing the empirical. 1 standard distribution, 2 standard distribution, 3 standard distributions. Okay, yeah, this one's quite skinny, but it's still symmetrical. Okay. It's got a mean, median, and mode that are all centered right there. And so therefore, we can just kind of consider everything at the mean being right here. So you can say that right here, the mean of adult men, okay, is 69.2. Now, just to let you know, remember 5 feet is 60 inches, okay? So whatever your height is, most of you are gonna be 5 foot something. Some of you are 6 foot, but like me, I'm 67 inches. I always thought I was like kind of small, but I'm not. If you really look at it, now I'll be honest, I don't know the standard distribution. This one doesn't tell you, okay? I can figure it out, but that's really not important for this lesson right now. But you can find out very easily. Hey, do I fit within 1 standard distribution? Oh, you're pretty normal. Remember, 2 standard distributions, still pretty normal. Outside of that, what? Things get weird. That's where your outliers, that's where the outliers live. But did you notice what I said though? Randomly, selected. These numbers were not just like, the person who did this didn't go, well, I'm gonna make sure to only pick these kind of people in this little general vicinity. No. He randomly selected people, and by that random process, this is the shape of the graph that came out of that. Just inherent. It just happened organically. And you're gonna see that a lot in statistics. Okay, things overall tend to always favor the normal curve. Nature favors a normal curve. Even when things don't make a normal curve, we can make it have a normal curve. You're all ex-college algebra students. You know of other distributions. Change the word distribution, let's change that word to function. You've all dealt with functions, okay? You've dealt with cubics, you've dealt with parabolas. All of those are a type of distribution, we could say. We mainly focus on logarithmic. Okay, you've seen those. Exponential, you've seen those. So think of that. And you've seen this. This will still sort of come into play a little bit. We kind of leave it behind now because we're going to start getting a lot more exacting with our measurements now. But it is good, something to always kind of keep in the back of your head. Always, at least let that be a skill you leave here with. That if you hear on the news and they start talking about standard deviations, just remember, hey, 1 and 2 standard deviations, they're trying to fool you. Just go, dude, that's normal. That's fine. You know, somebody says, man, that's a standard deviation away from me. You can go, who cares? That's normal. Well, that's a lot. No, really. It's not at all. You know, I know, my stat teacher told me. He said, chill out. So let's look at what some normal curves look like. You've seen this one, that's going to be it right here. We're going to start calling this a normal distribution because everything has been distributed around what? Let's see if you can see it before I actually give you the definition. What is everything distributed around? What is that big red line? The mean. Everything is kind of focused off that. It's almost like if I had sand and I was pouring out sand, what's happening? What happens to sand? It bundles up and then what happens? It kind of just starts falling off. And that's exactly what's happening with our distribution here. Can you tell it's symmetrical? That's important. That's going to be very important, especially for calculator use later on. Okay? But it's nice. When something's symmetrical, I like it. Because what it tells me is if something's happening right here, guess what? What if I don't have that information, but I know something's happening right here on the other side? Notice it's symmetrical. I can do some math to figure out, oh, what's happening on the mirror side of this? So you can always find out what's happening on either side. Okay? That's important. This, while being symmetrical, is not a normal distribution. Okay? It has to be that bell shape. Okay? Now it can be a skinny bell, it can be a wide bell, okay? But it has to be a bell shape. Are you with me so far? Okay. Super, super easy homework on this one, I promise you. Okay? Let me just draw on this real fast. In fact, I'll give you some homework help real fast. Can we all agree right here is my mean? Let me ask you a question. Just trust me on the artwork here. Would that distribution I just drew, would that have the same mean? Yeah, kind of obvious, right? That's a homework question. But still, now here's another question though. Would it have the same standard deviation? Why? Been crunched in, hadn't it? So the standard deviations are going to be really close to the mean. Okay. Notice the last one I gave you about the heights of mid. It was real crunched, okay? But look at one like this. What if I gave you one that did this? Does that have the same meaning?
Oh, it's expanding.
No, and it's been moved. It's not even at the same area. It's been moved over, hasn't it? Okay? That kind of help you see it? Like that is gonna be one of your homework questions. They'll say, hey, does this thing have the same standard deviation? Does it have the same mean? What do you think? And it's just gonna be like a little multiple choice, okay? Just because it's trying to get you to understand what a standard deviation, what a normal curve looks like. Well, we're good so far? Let me throw some calculus at you. Every single one of these, and you do not have to do calculus, so don't worry. I'm throwing it at you, I'm not gonna make you do it, okay? Every single point, and I'm gonna say perfect point right here. And I'm being very arbitrary, okay, so I'm not gonna throw the full weight of calculus at you. But if we're looking at this, notice each one of those little points are at a perfect spot, right? We know that because each one of those points will represent one standard deviation, two standard deviation, three, and so on and so forth. Do we only end with three standard deviations? No, they can go where? Infinity, yeah. It's just things get a little weird after this. Like, really, do we even count them anymore? No. We call these points inflection points right here. Okay? In calculus, it's where the shape of a graph changes direction. Okay? And so notice closer inflection points, as they move in, you're gonna have smaller standard deviations. Further away, you're gonna have larger standard deviations. Okay? Like I said, remember all this today, proof of concept. Okay? Area under the curve. Let me draw this a little bit better. You're gonna see this shortly, but look at my little line here. What some people might call a paradox, but it's not really. What's the area? What did I call this earlier? I said, remember this. I highlighted it and I said what? Normal distributions are also what? About what? Start with a P?
Probability.
Probability. It's all probability. Okay? Everything we're doing now is basically probability, but not like what you saw in chapter 4. We're gonna be going, okay, I'm rolling dice now. No, we're doing statistics, okay? When I do a statistics, when I do a sample, is that perfect? Is that completely 100% representative of whatever I'm studying? No. There's a probability aspect to it going, I think. Now, I don't like using the word I think, but I'm kind of helping you with it because remember, we're still doing experiments, okay? But I can say, I believe that the thing I'm studying has a chance of being in this vicinity, and here's what it is, more or less. Now, the more data we get, the more exacting we can be, okay? But notice, area under the curve, all probabilities equal what? 1. So notice here, the area under the curve, under this curve, under any normal distribution, area always equals 1. That's important. A little bit contradictory to what some people think, because I will have some students go, but what about this area here and this area here? Is that ever going to touch that line? So how does it have an area? You ever think about that? If it goes to infinity, how does it equal something? That's the calculus part. In calculus, you can have things go up to infinity and actually equal a whole number. Okay? So you still need to know that while this goes off to infinity, it still equals 1. In calculus, we call it a limit, so don't worry about it. Okay? But it does equal 1. We're good. That's going to be very important moving forward. Okay? Because everything is based off the area under this curve. You do not want to take area of this curve. Trust me. Which is where your book is going to come in 6.2. Okay? Or your calculator. Okay? Let's continue on. Let me give you some very important definitions that you're going to need to know. Like I said, I say no. Just hear me out. Will you need to know them completely in this class? Not really, because guess what? Anytime I say the word, I say me. Anytime Hawk says to you, normally distributed, you can understand immediately It's gonna fit everything I'm about to show you. It's gonna go by these rules. But for those of you who might go into education later on and using those graphs that they keep trying to send my wife, that I'm like, that's not the right way. Kind of makes me mad, but I'm like, whatever. But anyways, you can go, does my data fit this X, Y, and Z that needs to happen? Okay? A normal distribution. Once again, same definition is a probability distribution. Probability distribution for a continuous random variable, X. Remember how we did P of X equals X or greater than or less than? Defined completely by its mean and standard deviation. Such that the following properties, hence what I said, and I've said it 5 times, proof of concept. These are true. Okay, because if they're not true, why do it? Why do any of these tests? Why are you gonna learn any statistics after today? There's no point. I should be like, class is done. There you go. These have to be true. Now, like I said, they can be proven mathematically. I'm giving you the crib note version of a very long, and I had to do it, 15-page proof of why this works mathematically. Okay? The distribution is bell-shaped and symmetric about its mean. There's the mean. A normal distribution is completely defined by its mean. We're still dealing with population and the standard deviation. What it's saying is this thing is defined by its mean by saying it's going to start here. All the data is going to clump and then fall off. Symmetrical. And so we can define it by going, what does this standard distribution look like? Oh, there's the mean. Oh, here's my standard distribution. And if you do a little calculus, you could find your little inflection points and put how high the graph goes if you had to do that. Okay. Once again, the total area under the normal distribution equals 1. It should, because look, we're dealing with probabilities. Okay. And then the last thing, the x-axis is a horizontal asymptote, okay, for a normal distribution, or what you would call in calculus a limit. Okay. I say that because some of you will be going on to calculus after this. So there, planting a seed. Okay. Asymptote means what? It's never going to do what to the x-axis? Never going to touch. It's going to roll along and get closer and closer and closer and closer, but it's never going to touch it. It'd be like if I said, I'm going to go toward that door, but right now I'm going to go half the distance. And then I'm going to go half the distance again. And then I'm going to go half the distance again. Would I ever get to the door? No, because I'm always going to be halving my distance. You can actually look that up. That's called Zeno's paradox. Okay, that's kind of neat. You good with that? You just good with just going, okay, that sounds cool. I believe you. Thanks, math professor. Okay. Look at this. Now they skew our numbers a little bit. But look at this guy. It's a normal curve. If I took, now, let me correct my saying here. If I took a sample of some people in this classroom and I decided to take your IQ, it would not mimic a normal curve. Could you tell me why? I'm just doing this classroom. Let's say 10 people. Why would it not mimic a normal curve?
There'd be a lot of people in 2 different areas, or multiple different areas.
I think you're on the right track. So keep what you said. I like what you said there.
Like instead of, it would be shaped like instead of 1 going up, there'd be like 3 going up.
Yeah, you'd have 3 in the same area. Do you remember when I first started showing you like the dice? What happened whenever you were doing a sum of dice of like maybe after like 5 rolls? Could after 5, let's say 10 rolls, could I very easily get a sum of 2 4 times? Couldn't I? What happened as my number, that little n, went higher? What happened to it?
Became more constant.
Yeah, well, it started kind of leveling out, didn't it? Things kind of graduated toward what? It's classical probability. Same thing here. If I just did a sample of you guys and just do like say 10 of you, that's not a lot. But as my sample size does what? Goes up, what's gonna happen? It's going to approach a normal curve. I'm gonna prove this to you visually in two ways. One, at the gym. Okay, normal curves happen more than you think. I'll show you right now. That's a normal curve. Not a lot of people doing 10. Not a lot of people doing that. But look right here in the middle here. A lot of people doing that right there in the middle. Now, is it perfect? No. But it's getting close to one, isn't it? If you kept doing it over and over and over again, this is obviously a old gym, but still. And by the way, that's something a lady on Instagram, she does a lot of really good stat and physics stuff. It's funny. Okay. Also, if you look up on Reddit, if you look up bad stats, that's amazing. Okay. I look at it daily. Every single day I look at it because it's basically people who love statistics and they watch the news and they go, huh? And they take a picture and they go, look at what this guy, and they are merciless. Okay, so it's pretty neat. Okay, but notice the normal curve. It showed up, didn't it? Organically. Some guy wasn't sitting there going, hey man, put one at 10. Hey man, put one at 20. Hey man, put. No, that's just people just coming in, doing their thing. Coming in, doing their thing. It tapers up, it tapers back down. But let me go a little step further if you'd permit me. I believe this is gonna just start playing immediately. So what I'm gonna show you is what they call a Galton board. Okay, I used to have one and then it broke in my office at home. I've never had one since because it made a ton of a mess. Okay, you'll see why shortly. But think of Plinko. Okay, can we think of the lady's turn? What can we think of? Every time she did what? That was a trial, right? Well, what if I gave her a lot of trials? Not just one, not just two. What if I said, hey, how about I give you 1,000 Plinkos? What do you think would happen? Let's do it. Here's your Plinko board. Every hit is random. 100% random. This thing has been plugged in. It's got a random number. It doesn't know which way it's going to go. It is even accounting for, look, it bounces. That takes away the 50-50 aspect of it. And yet, look at what it approximates. Even if you wanted to take this and just go, what if I made it to where the ball hits and just falls? There's no bounce, but it just hits and falls. Couldn't you agree that that's 50-50, right? And then 50-50, and then 50-50. And look, we got, look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 2 to the power of 20. I'm gonna figure it out myself here. Scientific 1 divided by 2 to the power of 20 is 0%. There is a 0% chance. Let's just pretend like if we said these are heads. A left would be a head, a right would be a tail. Okay? There's a 0% chance of this being over here. If you actually look it up, it's a 0.00000009536. So there you go. But yet it did. So while there's 0% chance, I'm trying to show you, does that mean it won't happen? Yeah, look over here. Look on the other side, look far west. There is one that didn't happen. But yeah, right next to it, there's not just one, there's 1, 2, 3, 4. There are 6 little marbles in there. So your 0% chance happens 6 times. But it's still because out of the random laws of nature, and this thing has been, this thing right here is programmed exactly to be random, okay? It bounced, it has a certain, tension. There's not a 50-50. If you looked at it, if you played it again, look, some of these balls went here and did what? They bounced around. That mimics humans. Is everything you do, is it gonna be, if I take a sampling, is it gonna be, well, this or this? No. You're actually less random than this. Because if I'm doing a statistical study, I'm probably doing a study that says, hey, I'm testing a drug. Did you get better? Did you die? That's a 50-50, really. I mean, if you think about it, it's you're alive or you're dead. Right? That bounced around. I'm not testing bounce. Now that mimics a lot about polling because people are like, oh, but it still mimicked that normal curve. The thing I said, hey, this is proof of concept. I want you to believe in this as we move forward, because as we move forward, I start saying, because it's normally distributed, we can trust this statistic.
Does the fact that it's being poured down the middle affect it at all? So if they were all poured like in line, it would still somewhat mimic this?
Every time. You can do it one at a time. This would be like having a team of statisticians running out. Year one would be just you taking that. Okay? So it would still always mimic it. Now with this one, what kind of hurts it just a little bit? Those balls are interacting with each other. And so they are kind of pushing each other. But once again, isn't that the real world? Are you just an island unto yourself and just your own thoughts and you don't have any influence from anybody else ever? You're all on social media. You get influence. I watch the news. I get influence. I go to church. I get influence. I'm getting, my brain is that little ball being pushed around like this. And where am I gonna land? That can help you see it a little bit better. All right, let's do a couple of homework questions. They're super, I'm telling you, they are mind-numbingly easy. You're gonna recognize something on one of them too. Given X is equal to 34.8, the mean is 23.3, and the standard deviation is 3.9. Indicate on the curve where the given X value would be. On this question, it's gonna say, grab that mean and pull it to the right or pull it to the left. Would I be pulling to the right or the left? You're trying to find out where this guy's at. Well, if this is your mean, right? And this is just some sort of, okay, they're showing an arbitrary max. It can go a lot further than that, obviously, okay? Doesn't really need to. Would I be pulling that direction or this direction? Obviously that direction. I'm gonna pull it over and eventually you would get to probably right about here. And that's gonna be 34.8. Guess what? Hit the button, get the green bar, move on with your life. That homework, yeah, I told you, I'm getting face you're like, that's it? That's it. There is a method to the madness of this, you'll see in 6.2. Okay? It's getting you to understand where things are at on a normal curve. Now, hear how I'm saying that. Normal curve, normally distributed. Okay? All right, my little post-midterm people, what do you think you're gonna be doing up there? Z-score. Did I tell you, you're probably gonna be seeing that Z-score a lot? Okay, anybody remember the formula?
X minus mu divided by standard deviation.
Exactly, very good. X minus mu divided by standard deviation. Do they give me all that information?
Yes.
Yeah, so figure it out. Do your standard deviation real fast for me. I'll even put it in the formula. We have this 40. We have 36.3. And then we have 39.8. Be very wary of the rounding to the 2 decimal places. This is the rounding problems I saw. To round to 2 decimal places, you got to look at the what? Third. Okay. For your Z-scores moving forward, you want to write this down. You need to go to 4 decimal places. Okay. Or go to 2 right now, just go to 2. But you're gonna see why shortly. So right now, just write that, you're gonna have to go to 2 for sure. So it's going to put it to 2 for right now. I'm trying to think how accurate your graph, your thing is. Let me look at this real fast. Just trying to be very front for me. I'm very sorry. I like your spot. Okay, Z-score is gonna be 2. I'll show you what to go to 4. What'd you get? Give me a number.
I got 0.09.
Very good, 0.9. Am I gonna be pulling that to the right or to the left?
To the right.
To the right, you're gonna pull it over. Now you're gonna have to put the 0.09 there. Now, let me tell you right now, I don't know if it makes you put the number in and then pull it. Okay, you may have to put the number in and then move that this guy right here to wherever it equals 0.09. Okay? Beyond that, what is the Z-score? You can calculate it. You haven't wondered what it is the whole time? Is it? It's a standard deviation, but why is it 0? Because it looks to me like my standard deviation says 39.8. How come it gave me a 0.09? Sure, it's quite a small number.
Is that how far it is from the mean?
He's right. It's how far it is. Well, what does it mean? It's so it's standard deviation, isn't it?
Yeah.
Like, wouldn't I, if I said to you right now, what does it say for standard deviation up here? 39.8 is my standard deviation. Isn't that my distance from the mean? So how is 0.9 this distance from me? Notice my numbers aren't jiving right now. 0.09, 39.8. What if you put in 39.8? For your standard, what would happen? Do that real fast. We know the standard deviation is this, right? Okay, we'll find out the Z-score for that. 39.8 minus 36.3, okay? And what else we got here? Standard deviation, oh, I'm sorry, yes, I'm right. 39.8 and then minus your mu. Yes, and then divided by what? What do we get right there? I'm testing things right now.
Negative 36.3.
Yes. Why did that go to all of a sudden so hard? Let's find out in 6.2. We will not get all the way through it. What's the difference? Standard. That word. Standard normal distribution. If I compared you to another class of the same size, and would it be fair to say, to compare him and how his grade is compared to some other student in another class if I just compared them grade wise?
Probably not.
Think about it this way. If I took all of y'all's data, put it in my calculator, put it in Excel, I'm gonna get a mean. I'm gonna get a standard deviation. And then I could also figure out his Z-score of whatever his grade is on his midterm. And I could say, comparatively speaking, this is how far away he is from the mean. Okay, compared to this class. Now, what if I said, I'm gonna compare another student in that class to him, and his passing depends on how that student did. Does that sound fair? No. But what if I standardize this? Now I'm not looking at your data, I'm standardizing you and being able to compare two different things, but I standardize everything. Because could you agree that those two different classes would have two different means? They would have two different standard deviations. Things would be different, but I can standardize it where I could actually compare them both. And then make things more fair. And that's what we're about to do. We're gonna standardize all our normal distributions. Okay, we're gonna standardize our means. Where all the means will be the same mean, no matter what. Okay? Not as bad as what you think. There is your formula if you decided you want to take all your data and put it into a normal curve. Okay? You have one data point. You remember this is a function. Okay, so your function for X, if I did an 89 for a grade, I would put the 89 in here, plug it in here, do it all, and it's going to give me a point on my graph. And you would keep doing that over and 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 over again. Okay? And it will give you that. Good thing is you don't have to do that. Okay? But that is the formula for a normal distribution function. Okay? You need to see it. Okay? Once again, a standard normal distribution is a normal distribution with a mean of 0 and a standard deviation equal to 1. Should make sense a little bit, at least a little bit, because think about it this way. If I have a mean here, notice I haven't been saying a specific mean ever. I go, you have a mean, and I go 1 standard deviation. But this literally says, instead of that standard deviation being 39.5 or 6.2 or whatever, no, it's 1. It's now a 2. It's now a 3. We're standardizing it. Okay, so we can look at different standard deviations and have a way to compare them a lot easier. It is still equal to 1. Okay, and the x-axis is still an asymptote. So nothing's changed really for you right now, except for the fact is our mean has gone to a what? 0, and our standard deviation is now a what? 1. Well, 1, -1, 2, -2. It just depends on what side you're on. Okay? Let me show you. You'll be taking something that looks like the guy on the, well, for you, for the left side. Notice how you did it in the past. To find your standard deviation, you took your mean, you subtracted it or added it from the standard deviation. But now, when we standardize it, it's literally just going to become 0. -1 or +1. -2 or +2. Okay? Eventually, it will do it for you, but for right now, you're going to be doing it on your own. Okay? And let me show you what it looks like. I'm going to give you just one random one here. There you go. We are going to standardize this. And it's actually very simple because you're just doing a z-score. Do your mean real fast for me. What would be the data point at the mean? Where's the mean at? Yeah. What's my z-score? I'm going to tell you, go work it out. Put it in there. You got a z is equal to what? 25 minus what? 25. But you need what? What are you missing? Yeah, but don't I give you that? Look, there's an inflection point right there. There's an inflection point there. I know that's where 1 standard deviation is. So can I not come in here and go, well, it doesn't matter which side I use, but I can come here and go, how about 28.2 minus 25, and that's going to equal what?
3.2.
Oh, look, I have a standard deviation. Remember, this is not hard math. You all pass college algebra. Okay. Hey, what's 25 minus 25? What's 0 divided by anything?
0.
What's my mean got to be divided by? 0. Isn't that what my mean is supposed to be? A 0. So what do you think that standard deviation of 28.2 is going to turn into? Very good. Do it. 28.2 minus 25 divided by 3.2. Well, doesn't that just turn into, hey, 3.2 divided by 3.2, which is what? 1. That's what your z-score does. Now you've got something symmetrical. But now look, they give us this little random 27 in here. Find my z-score. What is it? I'm not doing this for you. Find a z-score and tell me what it is. On this one, I go to 3 decimal places whenever I do it in your notes, but for your z-score, once you start kind of like, hey, this is full alert, go to 2 decimal places for your table that you're gonna be seeing here shortly. Okay? You got a number for me?
625.
Very good. 0.625. And we want to run at 0.63. What is that telling me? Right here would be a z-score of 0.63, right? One of y'all said it is distance from what? The mean, okay? And you gotta be careful. Now, I want you to go ahead and keep thinking a distance on this, okay? But you do need to be a little bit careful because of where things are gonna start transitioning now, okay? What have I been saying a lot about the area and probabilities? They equal 1. Let me show you why z-score is important. You just found a way, because of some very smart people who liked you, have done a lot of the math for you, okay? The 19th century, you know, before calculators, some guy took that formula that you saw earlier, okay, and calculated almost all the infinite probabilities you could have at certain little points. A whole bunch of minuscule inflection points at every 10th, starting, I think, at -3 standard deviation goes all the way up to 3 standard deviations, and every 10th they calculated. They calculated the area of it, which involves doing an integral, okay? You're going to be reading a curve on in your book, or you can use your calculator, but I'm not going to use your calculator until you've had to use your books on. You have to standardize the given information it gives you. You cannot use the information that you've been given. Notice how earlier they said, hey, your mean was what, 25? Your 1 standard deviation away was 3.2, so plus or minus 3.2. Can't use that anymore. You're gonna have to standardize everything. Everything's gonna be based on this z-score now. Everything is based on this z-score now. So if you're having trouble with z-scores, don't. Go in there and start learning them, okay? So look here. Then you're gonna use the table. Now what they did for here is this. You don't want to do this, okay? This is an integral, okay? This says I need to take the area under a curve, okay? So what I would do for here is if I was going to do this integral, I would come here and go, I'm going to take the area from 0 to 0.63 and then put everything into that formula and integrate from there. And you know what that's going to give me? There's your z-score. But since you don't have to do the calculus of this, that z-score, when you go look it up on your little table at the very front of that book, gives you the area of that curve right there. Okay? The complete area. Why does that matter? Because when you know the area under the curve, that's the probability of that data up to that point. That's what that z-score is telling you. Okay? Yes, it's a distance from the mean, but we needed the distance from the mean to know how much area we're going to take under that curve. Okay? Kind of with me so far? Did it get just a little abstract all of a sudden? Like one step we were okay, all of a sudden it's like walking in the ocean. Next thing you know, you're falling, you don't know how deep it is. Okay, it's not that bad. Remember, everything is a probability. Okay? The probability of something happening under this curve is what? Something happening under this whole curve is what? One, it's a probability, it's one. So whenever you have a data point right here, okay, stay with me. Whenever I have this data point of 27, I know the z-score was 0.63, okay? I'm saying right now that the probability of some of my data, whatever I'm studying, whatever it is I'm looking at, being between here and this direction, okay, or less, is whatever area that's on my table. That's what it's telling me. So it's taking something discrete and saying this. What's the probability of me getting into a wreck from here to right here? Oh, it's this probability. We've turned something for that's not discrete, but continuous, because think about it, distances, that's continuous. Because I can say, what's the probability of me getting into a wreck here? Or here, or here, or here. Notice how exacting I can get, but now I can sum all those probabilities, all those little infinite inches, centimeters, millimeters, nanometers, into just one main probability, is what that area is telling us, okay? So let's do one. Let me show you how to use your table. We're gonna change this up to this. This person found a z-score. Can you see it? Now, can you also notice that that z-score, they are shading in an area, okay? So there is an area under the curve here, okay? Borrow a book. I'm not going to use the dot cam right now because I do have it. I won't lose your place again. You go to the very front of your book. This is what it looks like right here. You have, oh look, a little picture that looks like a normal distribution. Right here is the 1 and the 10th place. Okay, the 1's place, and then up here it'd be your like your 100th place. Okay, and that's why you do your z-score out to the nearest 100th. Your area. What do you think you're going to do area to? Huh? Why? Nope. Well, why would you? How many decimal places am I going to go to on the area? But why 4? What did you have to go through for your probabilities? You always had to go how many places? 4. What's area under a curve? So you go to, there you go. That's why you can, that'll help you remember right there. You're still dealing with probability. Everything is probability now, because remember, this is statistics. We don't, if I knew the population, I don't need statistics. I don't need probability. I know everything. This is saying, hey, the probability of this being under this curve right here is this. You're going to learn some error later on. Right now, we're doing some exact numbers, okay? So this is how this works. If you don't have your book, don't worry about it. But you're going to want to remember this. This is going to be in the video though, so don't worry. 1.37, notice I have, there's a table. Notice along this left-hand side here going down, it goes at 0.0 all the way to 1.3. At the very top, you're worried about the 100th place, okay? So I know I'm looking at 1.37. So look, 1.3 and 0.7, when you put those two together, you get 1.37. Good so far? Find where they connect, and there you go. That means, right there, that 0.9147 is telling me the area under the curve, right here, all of this is 0.9147, or let's put it in a way you'll understand it better. 91.47% of my curve has been filled in. How much has it been? How'd you find that out? Or 1 minus. Remember the complement? Remember I said, hey, that's going to come back. That complement's going to come back later on. There you go. That's how it happened. If you'll also notice, if you'll think back to the other one, remember we got 0.065 or 0. What was the other one? 0.625? Look here, here's 0.6. Here was 5, so. That one we just figured out, look, 74.22% of that curve would have been filled in.
Would it not be 6 and 0.03 because of 6
Oh, was it still 3? Thank you. There you go. Then go to right. Oh, that's 625, yeah. 62, yes, you're right. 0.63, so look, there we go. 0.7357% of our area was filled in. Now, I do say this, your calculator is gonna do a lot of this for you. There are sometimes your calculator is not fast, okay? Sometimes the table is gonna be a lot quicker. Good news. Final, I give you the table. Okay, every formula you're seeing here, not these calculus formulas. Okay, don't worry about that. I had to do that, one of those integrals, one time, only one integral, and I was like, I'm never doing this again, ever, because thank goodness there were smart people in the 19th century. Okay, but it's doable, and the calculator is real easy to use, and we're not done with this one today, but I don't want to get too far ahead. But do you understand conceptually right now what it's showing you? More or less. You don't have to have complete understanding. You can go, I think I can use that table. You're going to learn how to use your calculator well. You need to get used to understanding something. I saw a lot of people lacking on this, okay? Play with your calculator. Does everybody know how to do scientific notation in your calculator? Okay, if you look at your calculator, and I'm going to get does anybody have a calculator that I can just look at real quick? When you click on it to put scientific notation, you're going to need to look at, if you look above your 7 key, there is a comma key. But if you also look, when you hit shift, you'll see the letters EEs. Okay, that is scientific notation. First of all, does everybody know what scientific notation is? Okay. So that, remember whenever you do like say 5 times 10 to the power of 2, that's scientific notation. Except your calculator doesn't do the powers of 10 part, because that would look really weird, wouldn't it? If I showed you a whole bunch of numbers and then a 10 and then a power, that's a bunch of numbers. So your calculator substitutes the EE for that. So when you want to do an exponential, like say I want to do 1 to the power times 10 to the power of 99. Well, that's just a 1 with 99 zeros. That's a massively large number. You might want to remember that, because you're going to need to put that in later on, because when you start calculating area under a curve later on, using your calculator, at certain times, you're going to have what we call bounds. Did you see how my little integral symbol had an A and a B? Those are called bounds. That means I'm starting here, I'm ending here. Well, the one I just showed you, I started at negative infinity. I showed 0, but in actuality, I started at negative infinity, because why would 0 not work? What's my mean? Okay, so I have to start at a massively infinitely small number, which would be like negative 1 times 10 to the power of 99. Okay, and I calculate it up to a point. Now I'll show you this on your calculator, but I just want you to get used to knowing where it's at, so that when we get there, you're not like, what is he doing? What are those E's? You've already seen them on your test. Y'all probably got one that had like a whole bunch of numbers, and then had like E, and it had like a -9. Take that decimal, move it back. Remember, negative powers, we move backwards. Positive powers, we move forward, okay? So can I help you out a little bit? Yeah. So, like I said, right here, is there anything else? Nope, we'll stop there for today, and then